Okay, so I'll be telling you today about some work mostly done by Tom. Tom was a master's student. I say mostly because I'll tell you about some of the preceding work and some of the work afterwards, but mostly this is some work he did in his master's thesis. This is work with Calvin Tsai at Imperial London, Arthur, who's here in chemical engineering, and I had some role as well. Great. And now I'm going to really push the tech by...
There is no sound. Hello, hello. There's no sound anymore.
That. Do you hear me now? Test, test. All right, so
Yes,
get to the
yes,
point.
yes.
This is the paper. You can scan the QR code, you're done. This is it. So this is, as I said, Tom's work. And it was published a couple of years ago now in Computers and Chemical Engineering. So in some sense, it's an application of AI to chemical engineering, but I think that kind of undersells what Tom did. He really did AI, and okay, the use case was chemical engineering because that's a nice application for it. Okay, this one, no, this one. Old school tech. Let's just press the button here, shall we? Yes. Okay, good. So a little kind of introduction to why we want to do this kind of work, and then we'll get a bit into the technical details. So here we go. Here's someone, and she's working on, I don't know, some stock photo, but working on some project, doing something or other. Okay, what has she got? She has some objectives, things she wants, or at least we think, because these are often difficult to capture. Constraints, at least what we know at present, but usually these change. And there are some decisions. Usually we know what we want to do. Well, at least for now, until things change. So what are we going to do? We're computer scientists. Let's do something. What should we do? Let me see. Okay, great. We're going to produce some solutions. Let's just go for a technical, straight-on approach. We're taking into account these constraints and objectives, and we're helping maybe some decision support, this kind of thing. Great. Sounds like a very nice PhD project or three. Great. So we just need, a few PhDs to make the algorithms. There we go, great algorithms. And then, oh yeah, they should probably be not entirely slow. Depends on the time frame of the decision maker. Okay, but we can work on this stuff. Great. So we're kind of done, right? Well, you could just learn it. And this is what you see many papers try and do these days. Just throw machine learning at it, collect enough data, and maybe you'll satisfy the constraints, but you can fudge that a bit, and it can still be useful. And sometimes this is a useful approach. Indeed, we do this. Other times you want to do the kind of other side of the brain, which we do more inference over representations. So system one, system two thinking, deliberately slower. We're going to guarantee that we're going to satisfy the constraints. For example, let's say we're generating a program to do this. Your program, we guarantee, will be valid. Okay. But this is harder, right? Just throwing data at it is kind of easier, right? And then what do you do with uncertainty? Again, harder. So probably what we should do is we should do some combination of the both. We should put the two things together. Okay, so here's a survey outline of different ways people are trying to put together machine learning on one side and CO, combinatorial optimization, if you will, decision-making on the other side. So data and decisions. And so people do end-to-end stuff, as I mentioned. You can do augmentation. There's lots of ways you can do this in different types of optimization. You can try to predict things. We do combinations called predict and optimize. That's another talk. But what we're going to do today is this. We're going to do optimization to help machine learning. And you can see this little bit looks a bit lonely over here. Most of the action is down here, but there's little things up here. So this is what we're going to talk about today. Okay, let me see. So here we go. Here's our decision maker again. So what have we got? We'll have some pile of data. In this case, we know things about chemical molecules and engineering and boiling points. We know some stuff, right, about chemical engineering. So to put the two things together, run our nice algorithms, chug, 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 there we go. And there we are. Their computer says, do this. You investigate this molecule. That's what it says. Great. And so there's our solution. Good. Pipeline's clear. In principle, this is what you do. You have scientists plus data, some algorithms, everything's computer aided these days, and they shall Nobel Prize at the end. That's basically the high-level plan, if you're a chemical engineer. What's wrong with this? Well, nothing's wrong with it. The only question for the computer scientists, the question we care about as our bit of computer science is, how do we do the algorithm bit? Normally what you do is, you do stochastic gradient descent, right? You shove the data in, you call your Python package, it's doing SGD under the hood, you're done, right? Well, Tom's thesis, he said, well, okay, what if we don't do SGD? In this case, to train on, let's give it some neural network. But we're not going to train our neural network using SGD. We're going to train it using an exact optimization solver. So this is your system one. This is the normal thing to do. This is the system two approach. Okay. So we can use an exact optimization solver to train a neural network, in particular a graph neural network. Okay. This is crazy. Yes, it is crazy. It's not the normal thing to do, but it's not unprecedented. People started as far as back as 2018, even slightly before. There's now a whole industry of how to use optimization solvers to train exactly a neural network. You train it to perfection. And there's some advantages. You can do some additional things. You can do pruning at the same time, for example. You can do network compression. There are some advantages for doing this, as long as you don't have too much data. You have a massive ton of data, this approach won't scale. Okay, so here's the question for today. This is what we want to do. Can we formulate a graph convolutional network as an optimization problem, in particular in what's called a mixed integer linear programming? This is just a type of optimization. Hasn't seen mixed integer linear programming? Okay, doesn't matter. It just, it's an algorithm we're going to run. The key thing is it solves exactly the optimization problem you give it, provided you have enough time and you know what the problem is. Okay. I'm going to do a certain type of graph neural network. I'll get into that. Is the main objective clear enough? Okay. All right. Please stop me if you have questions. Otherwise, I'll keep going. So here's the outline. So first of all, we're going to do our formulations. This is the modeling side. Then we're going to look at another way of optimizing it, which is using genetic algorithms. And then we'll do some experiments on a particular chemical engineering task called boiling point optimization, which if you're a chemical engineer is very exciting. Sorry, I can't answer any questions about this part of the talk. I will show you the graphs, but I don't answer. Right. And first, we're going to do this thing called mixed integer linear programming. Actually, we have to be non-linear because it gets too complicated. Okay, so I'll talk a bit about this, and then we're looking at solving and some of the results. All right, let's get it started. So I assume everyone knows what a neural network is. Is that safe? Okay. This is a neural network. Okay, fine. We have layers, and you can have graph-like neural networks. I assume everyone knows what a graph neural network is. Okay, fine. Right. Okay. We're going to look at two flavors of graph neural networks, as I'll explain in a minute. Okay. So you can do it. You say, okay, let's write down this optimization model, lots of maths, for just like a normal neural network, a normal convolutional neural network. Okay. So as we saw on the previous, inputs, hidden layers, outputs, no graphs for now, just do the basic thing, right? Can you write this down? You can. You get this lovely kind of pages of things. And as a supervisor, when you see this, you just rejoice, a student's written this, and you look forward to reading it. And no. So it's very detailed, but it's, the squiggles work, you can do it. Okay, fine. So this is previous work. So Tom in his thesis said, can I do something similar, writing down lots of maths, but now not for just a kind of normal ReLU activation? Can I write it down for what a graph neural network would be in equations? Okay. All right. So it's not that complicated. Conceptually, what do we need to do? It's just a function, right? It's just a graph neural network, it's just a function. And so we can write it as a GNN, and we'll have some pooling at the end, and then an MLP, just to get a number out at the end. Remember, we want to do a boiling point prediction, so in the end, we're going to need some number. So this is known how to do. You can write this down in your equations. This is also that's straightforward. This is the new bit. Okay. So Tom was actually a student from maths. So he knows how to do the math stuff. That's great. So let's see. So what have we got? Let me explain. So A is your adjacency matrix. In other words, it's a feature vector. Okay. GNN is the graph neural network, obviously. And the point of these is mapping, as I said, to a single value. Okay. So here we go. So there'll be a quiz on this. Particularly, I want to know all the subscripts on the third line. So pay attention. No, I'm joking. So the graph convolutional network in the standard vanilla GCN, you can write down this kind of structure here. There's a bunch of matrices and you kind of do some multiplication, basically. Okay, fine, you can write it down. The key thing to note is this H thing with a K is somehow the next layer, if you will, of the network, or the next convolution of the network. So what we do next is some function of the weights and stuff and what we had before. This is how a neural network works, okay? And the layer after that, you take your current layer, you add some stuff to it, etc., etc. Okay, so you've got the structure. Can we write it down with the equations? You can. You get this kind of stuff. It's non-linear because of all those nasty things going on in there. So this would be a nice enough thesis, especially for a math student. He's taken a problem, he's abstracted it, a nice set of equations there. Great. But of course, he's doing his thesis with computer science and chemical engineering. So we say, great, this is good. That will pass you for your first stage review. We now actually want to see you code this and make it run. Okay. Can Tom do this? Fortunately, he can code. Okay. And the pooling stuff, etc. That's straightforward. Okay. All right. So what's the problem? I mean, you just code this up in Python, right? And then you put it into the solver. In principle, it's straightforward. It's just, there's nothing difficult conceptually of implementing it. Well, actually, there's one trick. You can't actually work these equations because it's a graph neural network and you don't know the structure of the graph. You know the adjacency matrix, but there's some of these terms here which you don't kind of know what they are. So it's kind of a mathematical detail. Well, here's the solution.
What do you mean? You said you know what adjacency matrix? What do you know?
Yes, so you know the adjacency. If I go back to the previous slide, in all these equations here, so for a MIP solver, you have some things which are known, so parameters, data, and you have some things which are variables it should solve for. But in this formulation, it's not well formed the way it is. And the reason is, in this thing here, we have to add an additional variable. It's kind of a mathematical
that is needed to transform it in
basically. So you have to add an additional Boolean variable here. If you know what Boolean variables are, fine. If you don't, it doesn't matter. But okay. There was a few hoops you had to run through. Okay, and then you can make it what's called bilinear. You want to do this because this is much better for the algorithms. These solvers work nicely when things are, you can compose them into straight lines. And bilinear, okay, the latest solvers can do this bilinear thing. This is much better for the algorithms. This is what it comes down to. Right, well done, nice trick. Okay, so that worked for a standard graph convolutional network. But Tom's ambitious. He wants to graduate cum laude. It's like, okay, not only can I do this, let's do some other types of graph convolution, graph neural networks. For example, graph sage. Are you all familiar with graph sage? Okay, so okay. It's another of the classic variants. It looks like this. Again, a bunch of H's and W's, so weights and layers, if you will. Looks a bit different. Can we do the same trick? Is he going to get cum laude? Yes, maybe. I don't know. It depends on the examiners. You can write down the equations. Great. In principle, we can do this. Okay. The details, it really gets messy, so I will refer you to the paper. Okay. Okay, so in principle, we're done. I mean, all Tom needs to do is implement it, which is, as I said, a bunch of Python coding, nothing difficult, and then he's going to run it on some benchmarks. He's going to graduate. So you can guess what happens. He implements the thing, and it just sits there. It's an optimization solver. We've given it now a well-formed optimization problem, and it will solve it. Maybe. Let's run it on Delphi. It's still sitting there. Let's run it for the weekend. It's still sitting there. Okay. So it's computational complexity. So in principle, it will solve it, but who knows how long. So the next thing Tom had to do was, well, let's try and help the solver. Let's try and inject a bit of knowledge to help it solve these problems. And what's going on is mathematically, the solver's basically wasting its time searching for stuff that's not actually going to matter. So we can do what's give it what's called some cuts. We can give it some information about kind of space to search in. Yeah, it's a known technique. He applied it, and this helps out quite a bit. Okay, fine. In particular, we have to do some stuff here and some more mathematical groups. Very exciting for the side if you're into this kind of stuff. Okay, so what did he do? He did what's called feasibility-based balance tightening, applied a known technique, and they did some domain-specific side constraints. Great. So adding some information, helping the solver, maybe we'll eventually get our graph neural network trained. You probably noticed I cheated here. There's a whole bunch of stuff going in here, but we'll come back to that. Okay, so yeah.
Is it one of the issues of not finding a feasible solution that you are creating feasible space?
Yeah, the main issue is the search space is essentially too large for the solver. And
but it's feasible, just too large.
Yes, computation. Yeah, it's just computation. I mean, in principle, we thought just run it for the weekend, it's done, you know, and fixed it on time. So in more detail, what's going on here is you look at these constraints and you say, okay, what's the smallest value you could have? It's a static analysis. And what's the largest value, roughly speaking? So you type in the bounds. And this, I say I cheated. This is things like, okay, we know that chemical molecules can't be less than 0 Kelvin. So we should probably say, don't go below 0. It's that kind of, there's some things going on. So this worked. I'll show you some results in a minute. So Tom could compute in his case study. So should we let him graduate? Well, I think that's enough to graduate, probably. He wants, he's quite ambitious. Can we do some more? What people actually do in chemical engineering is a similar approach where they use genetic algorithms. Why would they use a genetic algorithm? Who's familiar with genetic algorithms? Why would they use a genetic algorithm? What do you think?
Smart brute force.
Yeah. It doesn't guarantee to give you the exact solution, but we don't care. We just want some solution, right? It's a bit like doing stochastic gradient descent, but here we're not. Here people use GAs. Okay. So this is what we had before. Can we do something similar but put it into a genetic algorithm? Then we'll have two approaches. We can compare the two approaches. The answer is yes. If you know GAs, it involves some mutation, it involves some crossover. Can we do this? Apply this technique? We can. Okay, so actually what we're going to do is directly optimize using a simple GA. And so now Tom has his own approach and has a baseline to compare with. Very good. Should we also compare with using stochastic gradient descent? Yes, we'll do that too. Okay, details of how this works in the paper. Is there anything interesting to say about it? No. No. It's basically, we do it for graph neural networks. People did it before by converting them to a standard neural network. I think super interesting to say. Okay, let's try it. We're now going to try it on the molecular boiling point prediction. Okay, so this is your standard pipeline. This is what professional chemical engineers will do. They'll train a standard graph neural network using standard methods, SGD. So the idea is you do lots of experiments in the past, you know about lots of molecules, you use this data about all the molecules known to humanity, and you train a graph neural network. Why? Because this graph neural network can now predict or create or uncover unknown molecules in potentially. Okay? Why would you want to discover new molecules? For example, you want a vaccine against coronavirus or something. Okay? You want to create new therapeutic drugs, and therefore it's very interesting for big pharma to use this kind of computer-aided molecular discovery. Okay? And graph neural networks is what they use. The way they do this is often they will actually use a trained neural network inside a solver. Okay? I won't touch on that today, but because we can create these mathematical models of the neural network, we can use it in conjunction with other technology. Okay, so using computers, we predict new molecules, and then, okay, you get the output molecule, and if it's looking promising, you go to the lab, you synthesize it, expensive, slow, and you actually test it. Okay, so the better you can do the prediction, the less you have to do this lab-based stuff. Okay, in principle, this is fairly cheap. It's just computing. This is expensive and hard and slow. Okay, all right. So in particular, they're interested in predicting boiling points because you'd like to know things like, is your new vaccine going to be, have a stable at room temperature? This is useful to know, this kind of question. Does it make sense? AI for science, you could say. It's helpful, I can show you the, internet bodies are unstable. Okay. And we can see some results here. So here on the horizontal axis is essentially the size of the problem, the size of the network. So this is one layer of size 16. Okay? So it's bigger as we go. You might say, Neil, this is not a very large network. This is true. We're not going to be able to do large networks because of computational complexity. And this is the mean squared error, so lower is better. And here we're comparing the two approach. Here we're doing validation. The GCNs, the first thing we did is in blue, and GraphSage, the second thing is in red. We're just asking, will this thing work? Like, can we compute this thing and does it actually look at all feasible? And this is okay. The MSE is not too high, okay. And then you'll probably say, but hold on, didn't you say this is an exact approach? You guarantee me an exact, perfectly trained neural network? So how come you've got any MSE at all? I mean, can't you just overfit it on the training data? The answer is we have a computational limit. We can't run the solver for a year. We run it for 6 hours or something. Okay. So we do early stopping essentially. Okay, it works. Great, good. We don't do anything.
The exact part you'll guarantee on the training set, right?
Yeah, that's right. Right. And plus we don't want the thing to completion, so there's going to be some noise in there. Okay. So
what are the small circles you had in the plot?
These are outliers. So this is a box plot. Okay. So this is the average. This is the, somebody know, standard deviation. This is 95%. I know. Python, please plot this data for me.
What do we see as we increase the number of layers?
Yeah, so I'm glad you say that. Yeah. So as the network gets bigger, does the error kind of blow up? No, it's roughly the same. And this is nice. Yeah. So the limiting factor is not so much the size of the network, it's the amount of data. Yeah. The size of the network is, well, you look at the mathematical equations, it grows, but it's okay. But it's the number of data points that essentially kills it. And that's true for regular neural networks with this type of methodology. But as a validation, this is great. I mean, the thing works. It lives, it does something. Right? Solving time. So I mentioned we have a timeout. So here we go. This is now the running time on the x-axis, so low would be better. And we have a timeout of 36,000 seconds. What's that, an hour? Yes. 6 hours, thank you. There we go, 6 hours, right? And again, the size is on the horizontal axis. So this first point is of molecules of length 4. So there's 4 atoms in the molecule. Sorry, chemicals, I don't know. If it's the smaller size molecule, we can solve it quite nicely for 1 or 2 layers, but then it hits the timeout. We tried molecules of length 6, so medium size, and it all hits the timeout, which is fine. We still have some solution. It's just we don't know how good it is. It's not optimal. And likewise, the larger molecules. So this is a proof of principle. The thing works. Could you do larger than size 8? Yeah, maybe. Okay, not with this technology. Okay, but it's fine. It does something. That's the GCNs. Here's the optimality gap, which is how close are we to what we think the optimal solution is. The solver can tell us this. So again, low is better. The small one is looking great. The medium one, okay, it gets bad, and then the larger one. Okay, but this is what one would expect. Okay, right? That's for GCN. GraphSage, basically the same story. It's slightly hard. Automatic gap, yeah, so slightly hard. Okay, fine. We're not really going to use more than 6 hours of delve through for this thing. But, yeah. Okay, very good. Let's have a look at it side by side. So again, the blue one, I flipped the color, sorry. The blue one is the GraphSage, that's now on the left. The GCN is on the right. The message here is the GCN is easier to do, the GraphSage is harder to do. This you'd expect because the latter is a bit more complicated type of graph neural network. Right. Why that time? There we go. And here's what you've been waiting for. These are some of the molecules that Tom could find using his approach, using his training graph neural network. This is size 4, size 5. This is double bonds, triple bonds, etc. Like these actual molecules that his method can predict. And these molecules are all feasible with respect to the constraints, and they have certain properties about the boiling points, which is nice. Then the colleague in chemical engineering said, "Oh, this is great. What a nice plot. I'm so happy. Look, you're nearly graduated. Tell me, these molecules are any of these known to humanity? I mean, are you just reinventing the wheel here?" And it turns out that, I want to say almost all the molecules are things already known, like actually in textbooks we know about, but some of them are not. They're potentially novel molecules that need to be synthesized in the lab and so on. But Tom actually did some novel science here with his approach. Yeah.
How would you find what? Like, did you just try random combinations? And
Yeah.
So these are the ones that satisfy the constraints.
That's right. So I showed that slide with us, the standard pipeline earlier, and I mentioned you take your trained graph neural network and you put it inside some molecular discovery algorithm. In particular, you can actually put it inside a mixed integer programming. Now, because it has got a module inside it, and then you run that. So it essentially is a search, you might say. It's a search procedure.
It's be like sort of GNN IDIT search.
Yes. Yeah, that's right. Exactly right. So essentially, it's providing a heuristic which gives guidance to the search. But because it's a search where you can add constraints, you can constrain things like, I'm making this up, you can't put two of these molecules together because it's unstable, right? You can exclude it in feasible part. Things we know, physical constraints we know are impossible, right?
But in principle, do the same without the GNN input, right?
You could.
NLP.
You could, yeah. Yeah, and people use genetic algorithms to try and do it directly.
Did you see any benefit of using GNN search or anything else?
Yes. So now it becomes outside the scope of one master's thesis. But yes, so the nice thing is because you have the GNN, it's essentially doing a predictor. And because it's doing reasoning, if you will, over the graph structure, it can do things like, I think this type of connections between molecules is more promising. Right? It's being trained on everything we know from all the textbooks. And it's also doing prediction of the boiling points. So I think if you put this and this together, it's feasible, it's interesting, but I think the boiling point is outside our sort range. For example, the molecule would not be stable at room temperature. So it tries this, but you don't know until you actually, right. So it's doing prediction of these things. So yes, you can do without, but the nice thing is it gives you this kind of guidance, and therefore it leads you to hopefully more interesting molecules. Pretty cool. Right. So this one I've told you about, some nice mathematical modeling. Comparing it, I didn't go through the details here, to the standard genetic algorithm approach, and then some experiments which said this crazy idea almost works computationally and can give potentially promising way of doing scientific discovery. Okay, so that was old stuff. That was 2024 stuff. That's like, oh, come on, you know. So what did we do after that? So this is a graphs and data seminar. So I should tell you what we did after this. So next up was Sean. Sean was a computer science student who was very good at programming. He really was very good at programming, but also was sharp mathematically. And so what we did next was, okay, can we do the same thing of taking a type of neural network and training it mathematically? But this time, let's do transformers. People see what transformers are? Okay. So can we do transformers with this same approach? On the craziness scale, this goes up to like, 11 out of 10. It's a completely stupid thing to do. But actually, she got it working. It's nonlinear. It's very, very nonlinear and very complicated and extremely slow, but actually you can do it. And that was her thesis. I won't go into the details. We're working on writing up the paper right now. That was the next step. All right. What else to mention? So our colleagues at Imperial College London have a nice toolkit. If you want to play with these things, they have a nice Python toolkit called Omelette. Nice for doing this. And also they're applying other domain applications. Some of the other things we're doing is doing robust optimization with learning. So here, a bit less on the graph side, but again, trying to combine the data and the learning. And we're going the other way and using learning to assist the optimization, for example, using Power. So that's kind of this work plus extensions, and this is some of the other stuff that we're doing. That was it. It's never too late to scan the QR code. You too can read the paper.